So I'm looking forward to this next half hour with you. But look, I'm not going to go into too much of the deep science here, yeah, but like all good engineers, I've got some slides, yeah? So what I wanted to do is just the basics. What is superconductivity? You have to understand a bit about it just to follow the rest of it. So it's old, right? It was discovered in 1911. So it's relatively modern in terms of science and technology. But the key takeaways, it's very common. You have all interacted with superconductivity. If you've been to the hospital, you've had an MRI. If some of your bloods and other things have been analysed in NMR, even with cell towers, it is zero DC resistance, i.e. there's no power dissipation when you put a DC current down it. Why is it important? It allows incredible magnetic fields, much bigger than you can ever get with a rare earth magnet. They're talking about neodymium magnets. And stable levitation. That's a magnet levitating. It was taken a while ago, 2011, just levitating across a piece of superconductor. But the modern world relies on superconductivity. Why am I talking about it today? The world changed in 1987. And it changed when Bednorz-Müller discovered high temperature superconductivity. Something that was thought to be impossible at that time. In fact, I went to lectures where it said it was impossible. And literally when the Nobel Prize was announced for that, the lecturer came in and said, actually, what we said was wrong. It does exist. And why is it important? It's important for a number of reasons. It's important because it brings it back to where New Zealand have a link, a direct link into this technology. And why is it important? It's because it was material science. All of the other superconductors were metals. Cool them down far enough to liquid helium temperatures and they work. And that's what we're looking at down on the bottom right here. Helium is a scarce resource. It needs to be really, really cold. This sort of superconductivity is in, if you like, ceramic materials. And that allows you to use liquefied air, whether it's oxygen or the nitrogen. So actually we have no problems with the refrigerant cycle about how you do the cooling and how you work it. So really important. Literally across the water at the DSIR site, a team led by Bob Buckley and Jeff Talon developed one of the most commercial forms of superconductor, and they patented it in 1988, backed by Bill Robinson. So New Zealand actually are at the forefront of the application of this technology. Why? So what I wanted to bring us to is how and why is New Zealand different? Why are we driving things slightly differently to the rest of the world? It's not just that we were there right at the start. It's about driving it towards a purpose. And what is the purpose? It's something that Bill Robinson, the ex-director of DSIR, recognised, and which is why Robinson Research Institute take their name from him. That this material could absolutely change the world. It can change the world in that you can make generators and power systems that are a ninth of the mass, roughly a tenth, that you can actually have incredible power outputs. You can make things more efficient, higher power. And it even makes electric flight possible. But you have to put it into application. So there's plenty of good science, but we're good at actually trying to implement and taking it into application. So one of the things that I was brought in for was literally making the robot cable, the processes to make a cable from this material. New Zealand have worked not just on the materials, it's grown from a team of about half a dozen people to a whole industry in New Zealand now, but not just making the cable to make the generators, the motors, the windings, the other systems, but also to put it into application and recognise the benefits. Why should you care? okay? Why you should care is in New Zealand, we have a plentiful renewable resource for generation. We have 3 times our current generation capacity is consented from renewable sources. But the dirty little secret is all of our transport. Transport is dirty in terms of most of that is driven by imports of fuel. If we look at aviation, we are incredibly reliant, yet it's the growing sector in our emissions. That cryogenic superconductivity can, and the world acknowledges that, make a huge impact. It's where all of the big multinationals are focused. That 7% of our emissions from 2022 is still growing. COVID, people say post-COVID, our fuel imports for aviation, still growing. It's at higher levels now than pre-COVID. If we do that, we capture an economic benefit. It's one of the things that I've been focused on is how do we capture that benefit? And that's actually solved the challenge of putting it into practice. How do you process a thin ceramic into cables and magnets? We've done that. We ship all over the world from New Zealand. How do you efficiently cool these superconductors? We're still working on it, but we do that. And when I say we in New Zealand, we've gone out and we've trained a whole industry who are now capitalising it. How do you power them efficiently? How do you get thousands of amps into the windings and power those magnets? How do you protect them in these environments? Is there an export opportunity for lightweight, high-value products that are easily shippable? Let me see now. Things you can put in a container on a small aircraft for shipping. Yes, incredibly high value. So if we can grow that commercial and academic expertise, we're growing other industries. And we can spawn new industries and new technologies. That's been my focus. I could have talked about many aspects. I could have talked about certain technologies. I could have talked about how we power. But I thought actually the aircraft motor and generators embody some of what we're talking about. What I'm showing here is one of the aircraft motors that we're building. So New Zealand, you may not realise, already partners with big international players in helping them solve that challenge because of the technology here. At the heart of it, superconducting power supply, flux pump. IP is in New Zealand. That is a game changer, not just for those motors, but other industries. Integrated in, and we have demonstrated and integrated, which is why the world comes. Oh, sorry. Which is why the world comes. Optimised cooling systems. How do you not use a scant resource like helium, but actually a closed cycle refrigeration? How do you integrate the additive manufacturing? Now, I'm sort of glad that Ian Brown's here. Is he still in the room? Yeah, because actually he started some of this work. We've grown it with the industry in New Zealand. Additive manufacturing for multifunctionality, cryogenic materials, the power electronics. So to deliver this, I formed a grouping and through the advanced energy technology platforms. And I run that, and we've grown it as well with the industry and grown it much wider. But within New Zealand, it's a focus on mission-oriented research that delivering the solutions outside. You'll recognise the names. AUT with the additive manufacturing and with the cryocoolers, University of Auckland, power electronics. We start talking about what's happening with the University of Canterbury, Fabrum and the growth of Fabrum out of the cryogenic technology. Dodd Walls for the sensing, Callaghan Innovation on the cryocoolers, HTS 110, shipping magnets globally. We're growing a cross-discipline team in New Zealand. We have the best expertise in the world. We're developing the next generation of people who go out there and do it. That's why you see Tupakanga on here. Part of the things that we've done is we've grown a whole course at the diploma level. We've brought youngsters in. When I say youngsters, people during their degrees, before their degrees, and we've reskilled them to go out into that industry. We're growing the economy through seizing the opportunity. It's already delivering that growth, and it's already delivering that growth and contributing to a low emission future. Air New Zealand have a renewable and Sustainable Propulsion Test Centre in Auckland, right? They've invested massively into turning their turbine test centre just for sustainable propulsion. We have international developers coming here. We're integrating technology with Airbus. We're doing it with Pratt & Whitney and others. We're already delivering that, but we're also spilling it over and delivering that growth in other new industries. We do have a vision. We're making a difference in sustainable aviation. The industry comes here to New Zealand to solve their problem, and they do it because of what we've driven in terms of putting it into practice. Those challenges that we've solved are actually solving heavy transport in a much wider context. But that technology and IP is being leveraged to bootstrap other applications. If I said to you, some people have heard about it, that's the OpenStar levitating dipole. Actually, the team trained directly under me and worked with me on some of the technology and applied it to solve that problem and have done unprecedented growth. There's 65 staff now down at Naranga Gorge, demonstrated plasma last year. They're still growing. Our sensing technology that we developed is implemented not just with Airbus, but also at the heart of the Commonwealth Fusion Systems tokamaks in the US. The emerging liquid hydrogen industry and that whole industry links in. Some of the staffing and that training is linking in. As a reason, I spent a lot of time with John Kennedy at the back there, who's trying to hide. Those commercial opportunities are growing. Yeah. So, just like a good professor, I'm on the last slide in the last minute. So, one of the things is we've shown for that innovative technology use. I could have gone into a lot more detail on different parts, but it's about engineering into application to then leverage for the industry, and that's where we've been working. That technology spans domains of technology, science and engineering. There's commercial pull in multiple areas that New Zealand has critical expertise on now, and that expertise is growing. We are capitalising. We should continue to capitalise. We're at that point where we can take off in New Zealand and try to keep the development homed here in New Zealand. And that's one of the things I'm focused on, is how do we not just grow, but grow in a way that we're too big to be shifted overseas. Thank you.